before we continue our discussion, there are some small mistakes which are correct here. So this is 0 because it is on the x-axis. This is x plus the x on y. Similarly here also, this point is on the y-axis, so the x coordinate should be 0. Okay, so we were discussing random vectors. Now, we also talked about the PDF of a random vector, which is nothing but the joint PDF of all of its random variables. So it is a an n-dimensional random vector. Then there are n random variables, and we need to find the joint PDF of the n random variables. And we also saw the mathematical expression of the PDF, a Gaussian PDF for an n-dimensional random vector. Now, when two random vectors x and y are independent, their joint PDF So joint PDF means here we need to consider the joint PDF of all the x components and the y component. So if x is n-dimensional, y is n-dimensional, then we need to actually have 2n variables, and we need to consider the we have 2n variables, and we need to consider the joint PDF of all the 2n variables. So that is the joint PDF of two random vectors x and y. Now when x and y are independent, extending the same rule which we discussed for two random variables, we can write that the joint PDF is given by the product of the individual PDFs. So this is possible only when x and y are independent. Now what happens to this one? Expectation of x, y transpose. We wrote the expression for this one, right? X transpose. Now, just in place of x transpose, you just use x y transpose. So the second element is actually y transpose, but the expression remains the same way. We need to find the matrix. We need to operate the expectation operator on individual matrix elements. The only difference is that instead of x transpose, we have y transpose. But since we are applying the expectation operator, we can also write it this way: x, y transpose, and then we can take the joint PDF. And then we need to do multi-dimensional integration here, because both x and y are vectors. So I have just put 3, okay? It's not 3, you have more integrations. Now, in place of the joint PDF, you can write this one, correct? So if you write this one, you can group the x and y terms separately. So you can write this Again, each is a multi-dimensional integration dx, and then similarly you can write so this is the expectation of x, this is the expectation of y transpose. So we basically have the product of this and product of y transpose, right? So when two random vectors are independent, the expectation of their product is equal to the product of the individual expectations. So here we just need to do y transpose instead of expectation of y, we are doing y transpose. So if you take a y as n cross 1 vector, dimensional and n-dimensional vector, it will be just y transpose will be a 1 cross n-dimensional vector. Now when we can write this, that expectation of the product is the product of individual expectations, then the two random variables or random vectors are called uncorrelated. So whatever we have discussed here with random vectors also holds for random variables. Instead of taking x and y as two random vectors, you can just consider a single dimensional case, and then the same relationship holds. So when x and y are uncorrelated, the expectation of the product is given by the product of individual expectations. Now you can see that independence implies that they are uncorrelated. So when we say two random vectors or two random variables are independent, that automatically implies, which we proved on the previous page, that they are uncorrelated. But the reverse does not hold in general. So when two random vectors or random variables are uncorrelated, we cannot in general say that they will also be independent. So independence is a stronger requirement than uncorrelation or correlation. The only exception is the Gaussian random vector. In case of the Gaussian random vector or random variable, we can show that when they are uncorrelated, they are also independent. Just by using the definition, you can prove it yourself and show that when the random variables or random vectors have Gaussian distribution, starting with this implies that they are independent. The only exception for this is the Gaussian. Okay, so in case of Gaussian random variables or random vectors, uncorrelated means they are also independent. Now here, let's say that the mean of x is 0 or the mean of or the expectation of y is 0. Then what happens if one of the expectations is 0, then the product will be 0, right? Now when we can write this, which is a 0 matrix, if we have n-dimensional random vectors, it's basically a 0 matrix, all elements will be 0. When we have a single dimensional random vector or random variable, it is just a scalar quantity, 1, 0. So when we can write this, it implies that they are orthogonal. Now in the previous case, we see that when one of the means is 0 and they are independent or they are uncorrelated, they are actually orthogonal. But if they are orthogonal, that does not necessarily imply that they are uncorrelated or independent. So 0 means independent generated random vectors or random variables are orthogonal. Later you will see that the orthogonality principle is important in the context of estimation. Using the orthogonality principle, we derive some important filtering algorithms. Now, how do you interpret it geometrically? So, to interpret or to have some physical significance, let's consider this one, this orthogonality, and compare this. Let's compare this orthogonality of random vectors with the deterministic case. So, when x and y in the deterministic case, when x and y are two orthogonal random vectors, we know that x transpose y is 0, right? We know that in the deterministic case, x transpose y 0 means they are orthogonal, correct? Now, what is the equivalent relation for stochastic or random processes? Random case. So, when x and y are random, then we write this one. So, random means they can take any value. By doing expectation, we are actually interested in their average, the average of the product. So, only from the average we can draw some meaningful conclusion. Otherwise, it is purely random. We can't say anything about it. Now, you need to show that this also implies that so in this case, it is an n by n matrix. And when this is true, you need to show that a very simple proof that this also holds. And this we can compare with this one. So this is the deterministic relation of orthogonality, and this is the equivalent one for the random variables or random vectors. Because they are random, simply taking x transpose y will not give you any meaningful information. You need to operate the expectation operator to get the average representative value, and you will find that that average representative value is nothing but 0 when the two random vectors or random variables are orthogonal. Okay. So last week I gave you two homework problems. Both are easy. Today this is the first one. Again, this is an easy one. Next I am giving you another homework problem which is not difficult, but you need to think in a proper direction to find the proof. So you need to show that the covariance matrix, we defined covariance matrix last time, is positive semi-definite. What is the definition of positive semi-definiteness? So you basically need to prove that for any deterministic random, for any deterministic vector A, this one A transpose A is greater than or equal to 0, and this holds for any deterministic A. So this is the definition of positive semi-definiteness. and you need to show that a covariance matrix always satisfies this, and therefore it is positive semi-definite. Okay, so this is the fourth homework problem. And we are going to discuss all the homework problems next Wednesday. This Friday also we are going to have a theory class, no tutorial. But next Wednesday we will have a tutorial class where we are going to discuss all the homework problems. You need to first show what you have done quickly. Again, I want a methodical approach. Do not scribble something here and there and show me. Write them down neatly and then take screenshots and be ready with your explanation in advance. So that whenever I ask you, you can show that quickly. I already showed you model answers, so you need to follow that. Okay. Any question? Anything not clear about random variables and random vectors? Okay. Next, we are going to extend the concept of random vectors to random processes. These are also called stochastic processes. So how do you define a random process? Now if you consider a random vector which evolves in time, it becomes a random process. Okay. So in case of a random process, we do not simply write x bar. Instead, we write x bar and then its domain and then t. So time is another dimension in case of a random process. Right? Now for simplicity of notation, we drop the first argument, we simply write this x of t. Now since the random process evolves in time, if we sample it at different time instants, we actually get different random vectors. Here, by putting bar underneath, we are actually considering an n-dimensional process. So we have n, actually a collection of n stochastic random processes, and therefore if we sample it, we basically get n-dimensional random vectors. So if we sample at T1, we get one vector. If we sample at T2, we get another vector and so on. So basically by sampling a random process, we get a number of random vectors. So how do you get all the information about the random process? So to get all the information, we need the joint PDA. For all time instants. So T1, T2, T3, T8, T4 and so on, which we cannot get in reality. Right? So to find finding the joint PDF of the random process is practically impossible. So instead of having the joint PDF, what we do is we keep track of mean. It's denoted as mu. So this is the mean. So at different time instance, we need to get, when we sample, we get different random vectors, and if we take the mean of that, we get the mean. And we also keep track of the covariance. Now here we are interested in finding the covariance of two random vectors. One, let's say, sampled at t, another sampled at some other time s. Okay. And we are also interested in finding the correlation. And here we define the correlation matrix, right? See, this is the covariance, right? And similarly, we can also have correlation. I'll just write t comma s, because one random vector is sampled at time instant t, another random vector is sampled at time instant s. So this is the correlation matrix, this is the covariance, this is the mean. Now we also know the relationship of the covariance matrix with the correlation and mean. We proved this last time. So this one, the covariance matrix is given by the correlation matrix minus the mu transpose. So if we know the mean and the correlation matrix, we can find the covariance matrix. So basically we need to keep track of the mean and the correlation matrix. Okay. Now in this context, another process is of particular importance. It's called a wide sense stationary process. Its mu, the mean, is constant. It does not vary with time. So whether you sample the random process at T1 or T2 or T3, you will always get the same mean. Okay. Then the next one, the correlation. Of two random vectors, one sampled at t, another sampled at s, actually depends on the difference between t and s. So if you sample the random process at different time instance such that the interval is constant, and find the correlation between any two, you will find that as long as the interval, the difference between the two time instances is the same, you get the same correlation. So the correlation basically depends on the difference between the two time instants. So this we simply write as t minus s. So the difference between t and s is important here. Okay? As long as the difference remains the same, you get the same correlation. Okay? Now since here we have a process that evolves in time, just like a deterministic process, it contains important information in the frequency domain as well. We know that in the case of a deterministic process, by seeing the frequency domain properties, we can infer its behavior in the time domain. Even without seeing the process in the time domain, just by seeing its frequency domain properties, we can interpret important information or derive important information about the process in the time domain. For example, if we have a process which has a large bandwidth in the frequency domain, we know that the process changes fast in the time domain, it evolves fast in the time domain, right? Similarly, if we have a narrow bandwidth process, we know that it has a sluggish response in the time domain, right? In control systems, you have seen that by shaping the transfer function in the frequency domain, you can change its time domain behavior, right? So there is a one-to-one relationship between the two domains, time domain and frequency domain. By seeing frequency domain properties, you can quickly infer things about the time domain. In fact, you can also design the process without going into time domain relation explicitly, just by working in the frequency domain, as you may have done in your control systems course. The random process. But there is a problem. What is the problem? The problem is if you take the Fourier transform, the Fourier transform is, we know that the Fourier transform of any function x of t is to the power minus j 2 pi ft dt, right? And when we integrate it from minus infinity to plus infinity. So this is how we define the Fourier transform. Now when x of t is a deterministic signal, we have no issue. We just do this and we find the Fourier transform, and then from the Fourier transform we can do all our analysis. But if x of t is random, if you take its Fourier transform, that is also random. So instead of getting some meaningful information, what you see is some random pattern in the frequency domain. So from there, the random pattern, you cannot derive any conclusion. Now, what should we do? So we need to find some deterministic quantity for the random process, which will give us meaningful information about the process in the frequency domain itself. And we know that a good way to find deterministic properties is to apply the expectation operator. We already saw that using the expectation operator, we can calculate mean, variance, etc. Right? Even for a random process, we use the expectation operator to find the mean, variance, covariance, etc. Right? So somehow we need to operate the expectation operator in the frequency domain to make things deterministic, and from there we can derive some important conclusion. So let's see how we can do this. So we use a parameter called power spectral density for this purpose, for PSD. Okay. Now, before getting into the PSD, the power spectral density, let's define power. So we often say power. But what is power? How do we define power formally? So let's define power, and then from there let's go to power spectral density. Okay, and we are going to do this for a deterministic signal first, and then we'll extend that to a random case or a random process. Okay, so let's assume that we have a deterministic signal x of t. What is its energy? So energy is given by this one. We need to integrate it from minus infinity to plus infinity square, and then integrate over time. So by definition, this gives the energy of the signal. What is the problem with this definition? Now, if you have a signal which extends up to infinity, which does not decay over time, it has infinite energy. For example, if you consider a periodic signal, a sinusoidal signal, which exists all the time, it does not decay with time. If you calculate its energy, it is infinite. How will you distinguish two sinusoidal signals? Both have infinite energy. So there has to be some other means to distinguish these two signals. Now, although they have infinite energy, they can have finite power. Okay. So, the problem with the energy, why we cannot use energy for all our analysis, is that but they can have finite power. So often use power, average power. But how do I define power, average power? Now suppose we have this signal x of t which extends up to infinity and we truncate it. Okay, so we say that the truncated version is x capital T of small t and it is defined as follows. So it is equal to x of t when small t is less than mod t. Okay, so when small t is within plus minus mod t by 2, within plus minus mod t by 2, the truncated version of x of t is equal to the actual signal, but it is equal to 0 outside. So this is the truncated version of the signal x of t. Now in case of a periodic signal, this definition holds for both periodic and aperiodic. A signal can extend up to infinity without being periodic. It's not necessary that it has to have a periodic nature. So we can say that even an aperiodic signal, which does not have any periodicity, can extend up to infinity, right? And that signal will also have the same infinite energy issue as a periodic signal. Now, when it is a periodic signal, the T is nothing but its period. Okay. But if it is an aperiodic signal, then we can take some suitable time, capital T, and truncate the signal. Then the average power, P average, is given by this. So what we are doing, we are first finding the integration. Now instead of doing it from minus infinity to plus infinity, we are doing it over that finite interval over which we have truncated the signal. And then divide that by the interval length t. And then we let t go to 0. So this actually gives the average power. Okay, now in the case of a periodic signal where t is the period, you will find that when you do the integration and divide that by t, it has a finite value which is for a sinusoidal signal which is not dependent on t. So whether you let t go to infinity or not, it does not matter, because this term, the whole thing after dividing the integration by t, will not be a function of t. But that is not the case always. So in general, the definition is this: you truncate the signal if it is a signal which does not decay over time, does not go to 0 after a certain time. Truncate the signal over some time interval, find the integration as defined here, divide that by t, and then let t go to 0. Okay, so this gives the average power. Now, how do we go to the frequency domain? We are interested in the frequency domain. So how do we go to the frequency domain? Now, for this purpose, we are going to apply a theorem which relates the time domain integration to the frequency domain. So this is the time domain integration, and the theorem says that in the frequency domain, the left hand side is equal to this. So capital X of f is the Fourier transform of x of t d. Okay. So we are going to make use of this theorem, which relates the time domain integration to the frequency domain. Now, if you look at the integration carefully, you will see that although the lower and upper limits are t by 2, we can conveniently put infinity for the truncated signal because it is 0 outside this interval. Right? So let's do that. Now we can change the lower and upper limits because this truncated signal is 0 outside the interval. So whether you put minus infinity to plus infinity or minus t by 2 to plus t by 2, you actually get the same result. Next, we are going to replace the integration because here we have the same form as this one. We are going to replace this integration with the right hand side of this. So instead of doing things in the time domain, we are going to do the integration in the frequency domain. Okay. Now we know that this is the same as this one. And here in the integration, we don't have any infinity or anything. So the integration actually holds. When we are integrating from minus t by 2 to plus t by 2, it actually holds, right? The integration exists. The same thing we can say for the second expression also, because they are the same, right? Therefore, this one actually exists. The integration exists, right? And when the integration exists, we can actually interchange the limit and the integration. So we can put the limit inside. Yeah. And then on the left side we have power, right? Actually we are getting average power. Now I just think of the entire thing inside the integration. What can we say about this one? It is a function of f, right? Because we are actually doing the limit t going to infinity. So after applying the limit, it is no longer a function of t, right? So this is a function of f. So let's, and since this is for x, x, the truncated version of x, so let's just put x, because we are also taking t to infinity. So let's denote it as phi of f. Now what exactly we are doing? We are actually integrating this function over the entire frequency range, and that gives us the average power. So this is some sort of a density. We are actually having this phi for different values of f, and then we are, by doing the integration, we are actually calculating the area, and that area is nothing but the average power, right? So basically this is sort of a density, and this phi is called the power spectral density for a deterministic signal. This is the power spectral density, just like the probability density function. By integrating it over a suitable range, we get the probability of x lying within that range, correct? And the probability density also tells us in which region x is more likely, correct? Similarly, the power spectral density is sort of a density, because by integrating it, we get the average power. And it also tells us which frequency component will contribute more to the signal power, right? Okay. Now, for any realistic signal, the power has to be infinite. Energy can be, power has to be finite. Energy can be infinite, as we had seen for periodic signals. Energy is infinite, but it has a finite power. So, for all realistic signals, power has to be finite. Therefore, we have power spectral density and the distribution of the power spectral density, the variation of the power spectral density over the frequency domain tells us which frequency component will have more contribution to the power, signal power. In other words, it tells us which frequency component is more dominant. But for a deterministic signal, we generally do not consider the power spectral density because the Fourier transform tells us everything that we need to know. It is a deterministic signal. If you take the Fourier transform, that will also be deterministic, and that tells us all the things that we get to know from the power spectral density. So the power spectral density is not all that important, although it exists. It's not all that important for a deterministic signal. We generally do not calculate the PSD of a deterministic signal unless we have a specific requirement for that, because the Fourier transform tells us everything. But that is not the case in case of a random process. In the case of a random process, the Fourier transform is also random and it does not tell us anything because we only get a random profile. So the power spectral density is important for a random process. Now we also need to define the power spectral density in a little different way for a random process. So for a random process, the PSD phi is given as follows. Again, we truncate the signal for the process, let t go to 0, divide 1 by t, but instead of simply taking xt of f whole square, we apply the expectation operator. Because if you do not apply the expectation operator, again it will be random. So you apply the expectation operator, and this is the difference. So this is the generic definition of the power spectral density. Okay. Now for a White's and stationary process, we know that the autocorrelation is actually a function of the difference in the two time instants, right? So instead of writing t minus s, we represent that time difference as tau. So if these holds, if these exists, not whole, sorry, if these exists, okay, if this integration exists, then it can be shown that the power spectral density is the Fourier transform of the autocorrelation function. This is it. Okay. Now, what if this integration does not exist? If this integration does not exist, then the Fourier transform also does not exist. It can be shown that if this exists, the Fourier transform exists. So if this integration does not exist, then Fourier transform also does not exist. In that case, we have to use this definition. So this definition always holds. Whether a process is a wide sense stationary or not, the definition that we have shown here always exists. Okay, it's always there. But if the process is wide sense stationary and if the integration of the autocorrelation function exists, then we have a nice relationship between the power spectral density and the autocorrelation function, which is that the power spectral density is the Fourier transform of the autocorrelation function. For many processes that we use in estimation, this actually holds. Okay, so when it holds, we can use this. Now let's try to understand with the help of an example how the power spectral density holds information about a random process. So for this purpose, we are going to define a particular type of random process called white noise. You will understand why it is called white. Just like white light, which has all the entire spectrum of visible light, white noise, we will see from the power spectral density that it has all frequency components from minus infinity to plus infinity. So let's define white noise first. White noise is called white if it has zero mean, this is a zero vector. Okay. Now when the mean is zero, correlation and covariance are identical. So if you look at the expression that relates correlation to covariance, you will see that the second term is the product of mean. So if mean is zero, correlation and covariance are the same. So whether we write correlation or covariance, the same uh, matrix or same value will be. So let's define correlation. The correlation, in this case, it's a matrix because we have considered an n-dimensional case. You'll find that the correlation matrix is given as follows. You are considering two time instants, t and s, and in dimensions. It's a diagonal matrix. Okay. All the off diagonal terms are zero. Only diagonal terms are there. And in the diagonal terms, we have delta functions. Now, for simplicity of understanding, let's define this for one-dimensional case. So for a one-dimensional case, we just have one value, and that will be given as C1 delta T minus S. So this implies that when T is equal to S, the argument is 0 and we have C1. When T is not equal to S, we actually have 0. So C1 times delta of 0. When T is not equal to S, we have 0. So if we plot the autocorrelation function, let's say against S, we have an impulse or delta function whose scale factor is C1 when S is equal to T. Elsewhere it is 0. So only when S is equal to T, it has some value. Elsewhere it is 0. What does it imply? Physically, it implies that this process is not correlated with itself if you do not sample it at the same instant. Only if you sample at the same instant, so T is equal to S, it is correlated. Elsewhere it has 0 correlation. So it is purely random. So if you sample it at two different instants, when we say uncorrelated, it means that by seeing the random vector at one instant, you just do not get any information about the random vector at some other instant. They are completely uncorrelated in time. Okay, so we'll continue with this tomorrow. We'll see how the corresponding PSD looks, and from there we'll derive some conclusions. Okay, and after that, we are going to define C over N naught. You may recall that in the context of GNSS, I told you that C over N naught is an important metric for determining the signal quality environment, so that we have good signal reception or bad signal reception, that can be determined by checking C over N naught. Now we are in a position to define what C over N naught is, so we have defined C over N naught. Following this, we will move on to filtering and extinction. Okay? Any question? Fine. That's all.